Okay, so in your board, I've placed 3 documents with a variety of past paper questions, some of which we've seen before, some we haven't. So this is Max's board, and the papers live in this frame here. Okay, so if we zoom in, I've labelled them. This one here has got some additional questions at the end, which don't concern us. It was an error. They're chemistry questions for year 10, one of my other groups, but the rest of the questions are all about this topic here. You have seen some of them before they appeared on your test, and also we used them to practice earlier. But that's not to say it would be a bad idea to have a look at them. Okay, so it would be a good idea to have a look at them. So this paper here is about extension of a spring, and this is the one I'm going to go through shortly. And these questions here are linked to work done and how we design vehicles to try and prevent them causing injury to the drivers. Okay, that's all to do with transferring the work done in a crash away from the passengers and drivers and into the vehicle itself. So this is the document we're going to look at, okay, and it's the one that's got 31 marks, and you probably were given it in your lesson on the on Friday the 25th, although I wasn't there, so I can't verify that. Okay, so I'll look at this question now. So here we have a graph which by now should be familiar to you. It's the graph of extension of a spring, or length of a spring in this case, against the force exerted on it to make it get longer and longer. Straight away we can see it's a very straight line. Okay, so this spring has not been pulled beyond its natural length. It stayed within its natural length. So the question says, a group of students are investigating how a spring stretches when forces are applied to it. They measure the length of the spring and plot the results on a graph. Okay. It says use the graph to determine the unstretched length of the spring. Okay, so this is where the fact this is length comes into play and not extension. And we'll notice that at 0 newtons, where there's no stretch at all, then they measured a length of 10 centimeters. So that would tell us that the unstretched length is 10 centimeters. Okay. Use the graph and your answer to I to calculate the extension of the spring when a force of 2.5 newtons is applied to it. Okay, so first thing we need to do is to find where 2.5 newtons is. There's 2 and there's 3, so 2.5 is in the middle. If we then draw a line from that point towards our line of best fit there, and then drop a vertical line down, then that will tell us the length of the spring, but we need to remember that the question's not asking for the length, it's asking for the extension. Okay, so the total length is 35 centimeters, but we need to remove that 10 centimeters because we're looking for the extension, not the total length of the spring. Okay, so the extension is 35, take away 10, which is 25 centimeters. Question then moves on. It says, use your answer to part 2 to fill in the equation. Spring constant equals force over extension. Okay, so in the previous question, we were asked what extension 2.5 newtons causes. Okay, so the force here would be 2.5 newtons, and the extension that we've just worked out is 25 centimeters. Okay, although we need to be very careful because that's in meters there. So 25 centimeters equals 0.25 meters. Okay, so we need to be careful that we've got the right units. 0.25, so that's newtons, and that's meters. Okay, and so to ensure that we don't do anything silly with our maths, we're going to use a calculator, because you're allowed to use a calculator. 2.5 divided by 0.25 gives us 10. So the spring constant is 10 newtons per meter. Okay. Now, next question says the student adds another identical spring in parallel with the first one as shown in the diagram. They find that the spring constant is now doubled. Add a line on the graph to show their results. Okay, so if the spring constant is doubled, then we can expect the same force then you would get half the extension. Okay, so if we take, for example, 40, the length of 40 there, to get the extension of 40 centimeters, it took, actually no, 40 is going to be too much because it's not going to fit on our graph, is it? Okay, let's try 20. So for 20 centimeters, it took 1 Newton. So if we double the spring constant, double the number of springs, then to get that same extension of 20 centimeters, it's going to take 2 Newtons because there's twice as many springs, twice the spring constant. And if we assume that the springs start at the same length, then we can just use those 2 points to get us a steeper line. So this line is twice as steep. We can be confident of that because to get the extension of 20 centimeters, it takes twice the force because it's twice the spring constant and twice the number of springs. Okay. And if we move on to the next question. So this question is about a trampoline. So an engineer in South Wales makes springs for trampolines. A trampoline is an elastic disc that is connected to a frame by many springs connected in parallel. As you land on the trampoline, the springs stretch. The springs work to return to their normal length. The springs pull back against your weight as you land. The heavier the person on the trampoline, the longer the springs extend. The springs are tested to see if they return to their normal length after being stretched. The spring will be permanently stretched if it extends beyond the elastic limit point E, where Hooke's law is no longer obeyed. The graph shows how far a particular spring extends when forces are applied. Okay, so basically, if you overstretch a spring, if you put too much force on it, it won't behave in this nice linear manner, and this linear manner is what Hooke's law is all about. Okay, so the Hooke's law tells us that the more force you put on a spring, the greater the extension, and that relationship is linear. If you overstretch the spring, then it's no longer linear. Okay, so the first question says, use the graph to find the largest force at which Hooke's law is still obeyed. Okay, so that's this question up here. If we go back to our graph, we just need to find out at what force E is reached, the elastic limit is reached. And so we need to then track back to our force axis, and tells us that the force is 50 newtons. Okay, so the force at which the elastic limit is reached is 50 newtons. Each spring in one trampoline will experience a maximum of force of 58 newtons. We'll explain whether this particular spring is suitable for the use in a trampoline. So clearly 58 is more than 50. So if you were to use these springs, then very quickly they would become stretched, and therefore the trampoline would no longer return back to level. Okay, so no, because 58 newtons is greater than 50 newtons, where the elastic limit is exceeded. Okay, so you'd end up with a load of stretched springs which weren't very springy anymore. Okay, calculate the spring constant for this spring up to the point E using the equation. Spring constant is force divided by extension. Okay, so we can go back to what we've already used, and at this point here, the spring is still just behaving as Hooke's law determines, so we can use 50 newtons. And if we work out what the extension is that causes, by carefully drawing a ruled line down, okay, then we find it's 2.5 centimeters. Okay, now in this question, again, need to be careful. The spring constant is quoted in newtons per centimeter. Okay, so we don't have to convert in order to get the answer in newtons per meter. It's asking for the spring constant in newtons per centimeter. So we can just use those two figures there. So the force is 50 newtons, and the extension caused by that is 2.5 centimeters. And unlike the last question, this one actually starts at 0, 0, so the extension has already been calculated for us It's not the length of the spring that we've seen, it's the actual extension. Okay, so 50 divided by 2.5. Okay, so do that in our heads, but let's just make absolutely sure we get the right answer. So 50 divided by 2.5, 20. Okay, so the spring constant is 20 newtons per centimetre. Okay, so add a line to the graph for a spring with a lower spring constant. Okay, so if we look at the previous question, this effectively is a higher spring constant, therefore is a higher gradient. So for a lower spring constant, we would expect a lower gradient. Okay, so it's not specified where, so it doesn't matter as long as your gradient is lower, then that will be for spring with a lower spring constant.